Imagine a missile so fast that by the time radar detects it, it's already too late. In 1967, engineers working on America's experimental hypersonic aircraft ran into a wall, not a political wall, not a funding wall, a physics wall. A T Mach 6 times the speed of sound, the air itself becomes the enemy. Friction doesn't just slow you down. It tries to melt you. Temperatures along the leading edge of the vehicle exceeded 1000 degrees Celsius. Aluminum was useless. Steel was marginal. Even titanium began to struggle. For decades, that heat barrier defined the limits of high speed flight. And yet today, China claims it has operational hypersonic missiles capable of maneuvering at Mach 5 Mach. Shi, perhaps even faster. So the question is not, is it fast? The question is, can anyone stop it? And to answer that, we have to start from first principles, because hypersonic weapons aren't just faster missiles, they are fundamentally different engineering systems. Visual, timeline V2 rocket, ICBM, cruise missile, hypersonic, glide vehicle. For 70 years, missile technology has followed two dominant paths. Ballistic missiles extremely fast but predictable. Cruise missiles maneuverable but relatively slow. Ballistic missiles, like traditional ICBMs, travel into space and then fall back down along a predictable arc. Visual, parabolic ballistic. Trajectory diagram: they can reach Mach 20 or more, but once launched, their trajectory is largely governed by gravity and inertia, which means radar systems can calculate their path. Cruise missiles, on the other hand, fly low and maneuver around terrain, but they move at subsonic or low supersonic speeds and speed. In military systems, buys you one thing above all else: time compression. If a missile travels at Mach 10 instead of Mach 2, your interception window shrinks by 80. Detection becomes reaction. Reaction becomes panic. That's the strategic context. Driving. China's development of systems like the DF-17 and other hypersonic glide vehicles. But this isn't just geopolitics, it's a thermodynamics problem. Section 2: the physics constraint. Why Mach 5 changes everything. Purposing flight is generally defined as Mach 5 and above. But why Mach 5? Because above Mach 5, the physics fundamentally changes. At subsonic speeds, air behaves like a smooth fluid. At supersonic speeds, shock waves form. But at hypersonic speeds, something else happens. The air can't move out of the way fast enough. Visual. CFD simulation: shock layer forming over blunt nose. It compresses violently at the vehicle's leading edge, and compression means heat. This is not friction heat in the traditional sense, it's compressive heating. The kinetic energy of the airflow converts into thermal energy, the stagnation temperature. Equation tells us temperature rise is proportional to velocity squared. So if you double velocity, heat increases by 4 times. T Mach 10. Stagnation temperatures can exceed 2000 C. That's hotter than lava, which means hypersonic vehicles are not just aerodynamic systems, they are flying furnaces. To survive hypersonic flight, you need three things: shape, material, stereo, contra. Let's start with shape. Blunt vs sharp. Counterintuitively, hypersonic vehicles are often blunt. Visual comparison: sharp nose versus blunt re-entry capsule. A blunt nose creates a detached shock wave, pushing the hottest air slightly away from the surface. This reduces heat transfer. It's the same principle used in Apollo re-entry capsules. Now materials: aluminum melts at 660 C, titanium at 1668 C. Not enough. So engineers turn to carbon composite S, ultra high temperature ceramic ablative coatings. These materials don't just resist heat, some of them sacrifice themselves. They slowly burn away, carrying heat with them. S is controlled destruction, but China's innovation appears to focus heavily on hypersonic glide vehicles. Unlike ballistic missiles that arc into space, glide vehicles re-enter the atmosphere, flatten their trajectory, skip along the upper atmosphere at Mach 5-10. Visual skip glide trajectory animation. This creates maneuverability, and maneuverability destroys prediction models. Traditional missile. Defense relies on three steps: detect, track, predict, intercept. Point 4 ballistic missiles. Prediction is relatively simple. They follow gravity, but a hypersonic glide vehicle. It can change direction mid-flight. At Mach 8, even small lateral adjustments at those speeds result in massive changes in impact point. And there's another issue: altitude. These vehicles fly lower than ballistic missiles, which means ground radar sees them later. The Earth's curvature hides them. Visual. Radar horizon diagram at Mach 10. A missile can cover 1 kilometer in about zero point 0.3 seconds. If detection is delayed by even 60 seconds, interception becomes mathematically difficult, and that's before we consider plasma. At extreme speeds, ionized air can form around the vehicle. This plasma sheath can absorb radio waves. Redis. Radar signaturam compete tracking. It's not invisibility, but it is distortion. No engineering solution is free. Hypersonic missiles are extremely expensive, extremely stress, hard to mass produce. Manufacturing carbon composites is slow. Precision machining for hypersonic control surfaces is complex, and guidance at Mach 10. Tiny errors become kilometers. Then there's communication. Blackout due to plasma. You may not even be able to update guidance mid-flight, which raises a question. Are these weapons precise or simply very fast? There's also payload trade-offs. To survive heat, you add thermal protection. Thermal protection adds weight. Weight reduces range. Physics demands compromise. Stopping a hypersonic missile means solving the same physics problem. Interceptor. Missiles would need extreme acceleration, high maneuverability. The sensor some countries are pursuing. Directed energy weapon, space-based sensor, glide phase interceptors. Visual concept art, space-based infrared detection satellites, but interception windows are small, and kinetic interceptors must collide at closing speeds exceeding Mach 15, which is like hitting a bullet with another bullet. The defense problem is at least as hard as the offense problem. Hypersonic weapons are not invincible. They are not unstoppable. They are vulnerable during boost phase. They are limited by thermal loads. They cannot maneuver infinitely without losing speed, and they are expensive. In many cases, traditional ballistic missiles are cheaper and faster. Hypersonic systems trade raw speed for unpredictability. That's the real innovation. Section 8 Economic reality. A hypersonic missile likely costs millions, possibly tens of millions of dollars. Add R&D, add manufacturing facilities, add specialized materials. This is not a weapon you use casually. It's strategic, and strategic weapons are about deterrence. If both sides build hypersonic systems, we enter a new equilibrium, one defined not by speed alone, but by detection and response networks. So can anyone stop China's hypersonic missile? Technically, yes. Physically, it's possible. Practically, it's extremely difficult. Hypersonic weapons don't break the laws of physics, they push them, and in doing so, they reveal something fundamental about engineering. Speed is never free, heat is never optional, and every solution creates a new problem. China's hypersonic program is not magic. It is materials science. Aerodynamics and military strategy pushed to their limits. The real race is not about speed, it's about who can manage heat, prediction, and cost better, because in the end, nature still writes the rules, and engineers, no matter how ambitious, must obey them.